On this tape, we will look at radical expressions and what is meant by a radical expression being in simple form or to be simplified. Our approach for this study will be, we'll first decide what characteristics we don't want a radical expression to have. You might call those the no-nos of a radical expression. And there'll be 4 of those that we don't want to see in our simplified radical expression. And then we'll look at the means by which to get rid of such characteristics in a radical expression. And there we'll need some properties of radicals in order to do that. But the good news is there's only 2 such properties of radicals that we have to worry with. And then we'll look at steps or procedures to follow in order to accomplish this, in order to take a radical expression and remove all the no-nos, if you want, from the radical expression to put it into simple radical form, using only the properties, the 2 properties of radicals, and of course ordinary properties of arithmetic. And then we'll look at several examples of exercises that you may encounter in working with simplifying radicals. So here's the question again. What must be true for an expression involving radicals to be in simple form or simplified? Well, let's begin by looking just at some examples of radical expressions that are not simplified. So here are some. The square root of 25 is a radical expression that we will say is not in simple form. The 4th root of 16x, we would not want to leave our radical, or we would say at least that radical is not in simple form. And our practice will be to just as we do with fractions, we always like our fractions to be in simplest form. Well, we want our radicals expression to be in simplest form. So we wouldn't want to leave the 4th root of 16x like that. Same is true for the cube root of 125ab to the 6th. Likewise, the square root of 1/2 is not a nice way to leave a radical. Or the square root of ab to the -1. Here's another row of examples of radicals we would not want to leave. 1 over the cube root of 4, the square root of x over the square root of y, 5 over 1 plus the square root of 3, and 4th root of a squared, and finally the 6th root of x to the 4th. Well, let's take each of these examples and let's see what it is that is the no-no about it that we don't want. So first, again, there's the question, and the first 3 examples we had there, and I threw in another one here. Number 1, the square root of 864, 2, the 4th root of 16x, 3, the cube root of 125ab to the 6th. And the reason these are not in simple form is, number 1 says, no factors within an nth root radical can be perfect nth powers. That is to say, the reason these aren't in simple form is that in the first case, number 1 here, the square root of 864, within that number, 864, that radicand, there's a factor that's a perfect nth power. Now, what's n in this case? Well, n is 2. That is, there's a perfect second power, or a perfect square. Number 2 is a little more obvious, I think. There are 2 factors in that radicand. 16 is a factor and x is a factor. Remember, factor means multiplier. I'm talking about the multipliers of the radicand. This radicand has 2 multipliers. And the first multiplier, the factor, is a perfect nth power. N here is 4. This is a perfect 4th power. And we're going to say that this is not in simple radical form because it has a perfect 4th power within the radical. By within here I mean is part of the radicand. Within the radical is the radicand, and the radicand cannot have a factor that is a perfect, in this case, 4th power, and it does. So that is not in simple form. We've got to recognize when they're not in simple form in order to have any hopes of simplifying them. So let's look at the third example here. Here's a cube root. So now we're looking for perfect 3rd powers that are factors. Well, sure, 125, you should know, is a perfect cube or a perfect 3rd power, and it's a factor. 125 times a, so that's a factor. We do not want to leave perfect cubes, factors, within the radical. See any others? Yeah, b to the 6th. b to the 6th is also a perfect cube, and so this would not be in simple radical form if we left either one of those within the radical. Let's make sure on this first no-no, talking about factors within the radical being perfect nth powers, let's make sure we all are clear on perfect nth powers. Take a look at the pad here. Let's talk about perfect nth powers again. Perfect 2nd power. A perfect 2nd power, isn't that anything that can be written as a quantity squared, right? That's a perfect 2nd power. And here's a bunch of obvious perfect 2nd powers. 2 squared, 3 squared, 4 squared, and of course if you had variables, a squared, b squared, c squared, and so forth. How about perfect 3rd powers? Well, yeah, same thing. A perfect 3rd power is, or a perfect cube, is any quantity that can be written as some other quantity cubed. If you can write it as a quantity cubed, then it's a perfect 3rd power. The clearly 2 cubed or 8, 3 cubed or 27, 4 cubed, 64 is perfect cube, or in variables, those are perfect cubes. And we can go on down the list. Here perfect 4th powers look like that, and here are some obvious examples of perfect 4th powers. And then in general, a perfect nth power is anything that you can write, any quantity that you can write as another quantity raised to the nth power. 2 to the n, 3 to the n, 4 to the n, so forth. They're all examples of perfect nth powers. Let's look at this a little further. Here's some other examples that are maybe not quite so obvious that are perfect nth powers. Perfect square, c to the 6th. Is that a perfect square? It is if there is a factor or a quantity we can put inside here that'll give us c to the 6th. Well, sure. C cubed. By the power of a power property, that is, of course, c to the 3 times 2, or c to the 6th. It probably doesn't take a lot of thought to see that as long as we write an exponent with a factor of 2 in it, like this, that is, just change that 3, say, to a 4, and that has to be a perfect square, because surely I can write that then by the same property of exponents as the square of c to the 4th, or in other words, c to the 8th is a perfect square, or a perfect second power in this case. Or we could generalize this, can't we, and say that as long as the exponent is a multiple of 2, that's just another way of saying that has a factor of 2 in it, like these two examples, you have a power that would be a perfect second power. Well, can we generalize this a little more? How about perfect cubes? Well, look at the same example, c to the 6th. Isn't that also a perfect cube? Because I can write c squared inside, and now I'm cubing the second power of c, which is the same thing as c to the 2 times 3 again, or c to the 6th. And in other words, if I want a perfect cube, I need a factor of 3 in the exponent, don't I? So as long as you write an exponent that has a factor of 3, or another way to say it, a multiple of 3, say for instance 12. 12 is a multiple of 3, and so this must be a perfect cube, because I can write it as the cube of c to the 4th. What do we got next here? Perfect fifth power. Is m to the 15th perfect fifth power? Sure. Because, why? Because 15 is a multiple of 5. That is, I can write 15 as 3 times 5, which means then that's the fifth power of m cubed. Or in general, if you have any exponent that has a factor, a multiplier of n in it, then that power can be written as a perfect nth power, because I can now replace inside the parentheses, in this case it would be x cubed, and write that as a power, nth power of, in this case, x cubed. So that's a perfect nth power. So every nth power has to have in its exponent a factor of n. Now let's look at the other no-nos that we don't want a radical expression to have. Here's the second one. Says no fractions or negative exponents within a radical. Here's a couple examples of that. Square root of 1/2. Well, the radicand there is a fraction. And the cube root of ab to the negative 1, the radicand there's obviously got a negative exponent. I went ahead and took an attempt to simplify it maybe. You might think, well, make it a positive exponent, but look what it happens is it turns it into a fraction, and that's a no-no as well. So, what about the third no-no? Well, let's move that out of the way, and here it is. Number 3 says no radicals in the denominator. And here's a couple examples of that. First one, square root of x over the square root of y, 1 over the cube root of 4, and 5 over 1 plus the square root of 3. What's wrong with those expressions is that they each have a radical in the denominator, and we will always, at least in this study, want to remove those from the denominator to put it in simple radical form. And finally, the fourth no-no is a little complicated in words. It says no common factor other than 1 between the index and the exponent of the radicand. Well, it's easier to see with the examples. Here's a couple of examples. Let me remind you with these terms. Index. The index of a radical, in this case, the index is 4. And the exponent of the radicand, well, a to the second power here is the radicand, and its exponent is 2. And it says that no common factor other than 1 between those two numbers. The index is a number and the exponent is going to be a number. We will say that a radical expression that has a common factor between its index and its exponent of the radicand is not in simple form. That is, there's a simpler way to write that, and we'll choose to write it that way. Same thing here about the 6th root of x to the 4th. Obviously, 6 and 4 have a common factor of 2, and so this is not in simple radical form. So let's summarize, put all this together, and let's look at the 4 no-nos that we now have that we don't want a radical expression to have in its when we have it in its final form. It says a radical expression is in simple form if 1. No factors within the nth root radical are perfect nth powers, so no nth power factors. We don't want that in our nth roots. No fractions or negative exponents within a radical. No radicals are in the denominator, and no factors are common to the index and the exponent of the radicand. So the procedures that we're now going to look at have got to eliminate all these characteristics from any radical expression that we encounter. Okay, well, before we start developing the procedures to simplify these radical expressions, we need to discuss the properties of radicals, and as I said earlier, there's only 2 of those. Let's look at them. Basic properties of radicals, and I'm going to state these for nth root so that we'll have them in general. The first property says that the nth root of AB equals the nth root of A times the nth root of B. Or you can say that in words another way, the nth root of a product is the product of the nth roots. And this is not hard to justify even with our study of rational exponents. We can see that this is nothing more than a version of one of the properties of exponents, because remember what the nth root of AB here means. You can always take the radical, the nth root radical, and change it to quantity to the 1 over n, and whatever's in the radicand becomes your base. So this the left side of this property can be written like that, and the right side of that property, we can do a similar thing for both these 2 factors. Take the first factor and change that nth root radical to quantity 1 over n and put its radicand as the base, and do the same thing for the second factor, and you get this statement. Now, is this statement true? Why, sure. If we were talking about just good old integer exponents, AB to the mth power is equal A to the m times B to the m. It's that third property of exponents. The power of a product is the product of the powers. And so the nth root of a product is the product of the nth roots. That's property number 1. And a similar property of radicals, and the last one really that we need for this is the nth root of A over B is equal to the nth root of A over the nth root of B. Or again said in other words, the nth root of a fraction is the fraction formed by the nth roots. Or some people like to say it, the nth root of a quotient is the quotient of the nth roots. And again, just as in number 1 there, you can you can justify this by, if you change it all to exponents, that left side can be written like this, so, and the right side can be written as a fraction of 2 powers of 1 over n, the top one being the a to the 1 over n, the bottom one, or the denominator, being b to the 1 over n. And again, that's just a special case of the power of a quotient is the quotient of the powers. So now we're ready to develop the procedures which we can simplify these radical expressions and remove these no-nos using these, essentially, these 2 properties of radicals that we've discussed. One additional provision we want to make here, and you've probably discussed this in an earlier study here with radicals, and that is to simplify our consideration of the nth root radicals that we're working with. We're going to make the assumption that every variable we encounter here represents a positive real number. And recall for a moment what that tells you about, if you look over at the pad a minute, what that says is, remember, if I tell you that A is a positive or a non-negative, you can include 0 in this as well, then when I talk about the nth root of a to the n, I'm assured that that's going to be a in all cases for all n, no matter what index we're dealing with. We're eliminating the complication here of when we have an even index, that says even, and a is raised to that even exponent, such as the fourth root of a to the 4th power. Remember, we want this to be always a positive number, and when a is anything, especially a negative number, then we can't be assured that it's going to turn out to be a. We have to put absolute values around it. Well, we don't want to have to do that in this discussion, so we're going to make the assumption that a is non-negative, and then the 4th root of a to the 4th will be a. So with that provision, then let's turn our attention to some exercises in which we'll, in the process of solving, we'll develop the procedures for simplifying radicals. So let's look at this first one. The square root of 864. I want to write this in simple radical form. So my no-nos are those 4 things that I don't want this radical expression to possess as characteristics. Well, some of them are obvious that it doesn't. There obviously is no fraction under the radical. There's no negative exponents under the radical. There's no radical in the denominator. This is denominator is understood to be 1, and the only other one besides the dealing with the indices, which we would check out maybe at the end here, is does 864, or can 864 be written as a product with a factor that is a perfect square? In this case, since we're dealing with nth root. And in this case, the nth root is, or n is 2. We're going to be using this property. The nth root of ab is equal to the nth root of a, the nth root of b. It might be worth writing it in terms of just 2 here, that would say then the square root of AB is equal to the square root of A times the square root of B. Now, I'm going to take a little extra time on this first example just to make sure everybody is clear on this. So we're going to first do this one kind of in a scenic route, and then we'll come back and do it a little more efficiently. But here's what, and this would be a perfectly legitimate way of doing it. It's just kind of long and unnecessary. But it might occur to you, looking at this, that 864 has a factor of 4 in it. That is, you can write 864 as the product 4 times whatever it takes to give you 864. Well, I happen to know it's 216 since I worked it out. And so I can write that as that product. And here's a no-no, because we know 4 is a perfect square, and we said that we don't want perfect square factors under our square root radicals. And so I want to remove it. Well, this property allows me to do that, because now I've got the square root of a product, and the square root of a product is the product of the square roots. So I'm going to write this as the square root of 4 times the square root of 216. And I know the square root of 4. That's the principal square root of 4 is 2 times the square root of 216. But, wait a minute. The square root of 216, the Radicand 216 may have a factor that is a perfect square. And son of a gun, it does, doesn't it? In fact, we can write it as 9 times 24. It's one way. And I know 9 is a perfect square. So again, this property says that this radical can be written as the square root of, or the product of square roots. And so I just applied this property again. And the square root of 9, I know is 3. Notice this is all multiplication. That's 2 times that. This is square root of 9 times that. So all I've done is simplify this square root of 9 to 3, because I know what it is. And let me just go another step and write that as 6 times the square root of 24. But are we done still? No, because 24 is not in simple radical form. Because we can write 24 as a product 4 times 6, where 4 is a perfect square factor again. And so we're almost there. I can again apply that property, square root of 4 times square root of 6, using that property here that the square root of a product is the product of square roots. And I know the square root of 4 is 2. And I'll just do this, error up. And here I'm going to write 6 times 2 times the square root of 6, or 6 times 2, that's 12 square root of 6. And now, are we done? Well, we've already checked out the 2 of the no-nos. We have now made the Radicand 6, and certainly no perfect square factor in 6, and we can't write that Radicand as a power that has a factor of other than 1 with the index. So we're done. That radical is in simple radical form. But let's do that a second way, and not quite so long. The approach I want to take is to try to gather up all the perfect squares and find the biggest one to start with. If I can find the largest perfect square that's a factor of 864, then I can do this really in one fell swoop, so to speak. So let's do that. And it might require that you do a little factoring off to the side to come up with that. And as you may have to take 864 and divide it out into its, even maybe into its prime factors to come up with that. But however you might do it, I'll write it down just in a factor tree. 8 and 108 occurs to me. And of course 8 is 2 cubed, so that one is in prime factors. 108 can be written as 2 and 54, and 54 is 6 and 9. 6 is 2 and 3, and 9 is 3 squared. And so now put all your factors of 2 together. There's 1, there's 1, there's 3. So this is 2 to the 5th power, and here's 1 3, and there's 2 3s, so that's 3 to the 3rd power. And now from that I want to write it as a product of the largest perfect square I can make out of these prime factors. Well, remember our discussion about perfect nth powers. As long as I take a exponent that is a multiple of 2, that has to be a perfect square. And 3 squared is a perfect square, and what I'm left with is 2 times 3. Now just multiply this together. 16 times 9, that's 144 times 6. So we can write, and I'll just do it down here, I can write the square root of 864 as a product 144 times 6, and now I'm going to use this property, the square root of a times the square root of b, the square root of 144 times the square root of 6, and I know 144 is a perfect square. In other words, I could write it as 12 squared, just to emphasize the point, or the square root of 12 squared is 12 times the square root of 6. Let's look at this one. This might suggest further how we can streamline the approach to simplifying radicals. Okay, remember now what we want to do is be sure that no perfect, in this case, 4th power factors are left within the radical. Well, obviously sitting right there is a factor that's a perfect 4th power, but y to the 12th, that exponent's got a factor of 4 in it, so we know that's a perfect 4th power. And 81, well, yeah, let me just write that over. We know 81 surely is 9 squared, or 3 to the 4th. So here we have a radical in which every factor in that radical is a perfect 4th power. Now we could emphasize this by, let me go off to the side here, and writing it as quantity to the 4th power. Couldn't we? This would be 3 times x times y cubed. And anytime you can write a nth root radical as a power to that nth power, then I know that radical is just the base that you're raising to a power there, 3xy cubed. In other words, that the nth root of a to the n is a. But I don't even have to do this. If I keep in mind that any time I end up with a radical in which I have a product of perfect nth powers, in this case a product of perfect 4th powers, I can come up with exactly the same expression by simply taking the fourth root of each factor individually. The fourth root, what I'm really doing is using the property of radicals and breaking this up into 3 individual fourth root radicals. And the fourth root of 3 to the fourth is 3. The fourth root of x to the fourth is x. And the fourth root of y to the 12th, well, look, it better turn out to be y cubed, which suggests that there's a real handy way to find the fourth root of any power that is a multiple of 4, just simply by dividing by the index. And so 12 divided by the index 4 is y cubed. Of course, you could take the time to rewrite it as a power of 4, do it that way. So we want to get to this point, and I think your instructor will allow you to do this, that the fourth root, you could just immediately say that the fourth root of 3 to the fourth is 3, the fourth root of x to the fourth is x, the fourth root of y to the 12th is y cubed. Now let's take that approach with this one. I want to write this as a product of cube roots. The first radical having perfect cubes as factors underneath the radical. Well, the cube root of 125ab to the 6th, well, I know 125 here is a perfect cube. It's 5 cubed. And I know b to the 6th is a perfect cube because 6 is a multiple of 3. And that's all I can do. And so a is left over here. And I've got a product of perfect cubes. And a product of perfect cubes is a perfect cube. But we don't have to write it that way. We can just take the cube root of each factor individually. The cube root of 5 cubed is 5. And the cube root of b to the 6th, again, one way to think about it is just to divide 6 by 3. And so that is b squared times the cube root of a. And now, always check yourself. Is that in simple radical form? No perfect cubes factors left in here. No radicals in the denominator. No fractions or negative exponents within the radical. And my exponent and my index have no common factors other than 1. Okay, why don't you try this one and pause the tape, and then after you finish, start up and we'll work it together. Okay, so I think the first thing I'm going to do here is factor that coefficient, 128. Well, 128, again, if you need to go off to the side to do something like that, one way to do it is just start dividing by the smallest prime number it's divisible by, and keep going until you run into something you recognize. Well, 64 you might recognize is 8 times 8, or 2 cubed times 2 cubed, that's 2 to the 6th power. And so we've already got a factor of 2 here, so this must be 2 to the 7th power. Alright, so we can rewrite this then as the 5th root of 2 to the 7th power, x to the 9th power, y to the 12th power. You can, if you do it this way, you can treat your number factors exactly the same way you do with your variables. And now I want to write this as a product of 5th roots And in the first radical, I want only perfect fifth powers. Well, that means I want exponents that are multiples of 5. Well, the biggest one that's a multiple of 5 that's less than 7 would be just 2 to the 5. So that would leave me 2 squared to put over in the second radical. X to the ninth, well, would have to be, again, 5 is the exponent, and leave me with x to the fourth in the second radical. And y to the 12th, multiple of 5, y to the 10th power, and that would put y squared over in the second radical. And so what I have in the first radical is a product of perfect fifth powers, which has to be a perfect fifth power, and we can take the fifth root of it simply by taking the fifth root of each factor. The fifth root of 2 to the fifth is 2, the fifth root of x to the fifth is x, and the fifth root of y to the 10th is y to the 10 divided by 5, or y squared, times the radical we're left with here, the fifth root of 4x to the fourth y squared. And again, check the other no-nos and you'll find that that is in simple radical form. Okay, next one. Cube root of negative 81 m to the 10th power. Again, you may want to try this one first. All right, let's do it together. So first we write it as a product of cube roots. Take the coefficient first. Can we take a perfect cubed out of negative 81? Yeah, we can write 81 as 3 to the fourth. So negative 81 would be negative 3 to the fourth. I'm going to choose to write that as negative 3 cubed times 3. And that'll leave me with 3 underneath the other radical. And then m to the 10th, m to the 9th is the largest perfect cube, in 9 being a multiple of 3, leaving me with m. And then taking the cube root of each of those perfect cubes, that's a negative 3, m to the third power times the remaining cube root radical, cube root of 3 m.